All right, everyone. Um, so let's settle down and maybe get back to where we were talking about before the quiz last Friday. But before I do so, any feedback from the quiz? Hard. Okay, yeah, I see that most of you were scribbling all the way to the end, so must have been a little long. I was hoping it wouldn't be, but I'll see how it turns out. Um, All right. So other than that, Dr. Liu wasn't able to make it. She had a doctor's appointment today, so she won't be holding office hours this afternoon. But I'll hold office hours tomorrow. And homework 5, which actually has a couple of questions very uh, common from your quiz, is already posted on Blackboard. Please do note that on the quiz, those two problems you were meant to solve with the virtual work method, but on the homework, you need to use the Castigliano's theorem to solve the same two questions. Okay, so again, the procedure might be slightly different, but the numbers uh, and the steps will actually turn out to be exactly the same. But still, you have to show that you're using the Castigliano's method. Okay. Any questions on any of the lectures or the quiz or the homework or anything else? No? All right. So we'll get back into the force method that I had started before the quiz last week. So just to refresh your memory, we are trying to solve indeterminate systems, indeterminate structures. And I told you that the key thing about indeterminate structures is that the response depends upon the material properties of the structure, right? If I was giving you the example of two springs hanging by the ceiling. If one is stiff, one is soft, then the stiff spring ends up taking most of the load. So that's going to be something that you need to keep in mind. For indeterminate structures, equilibrium alone is not enough. You need to use material properties and you need to use compatibility to solve those systems. I gave you a couple of very simple examples of a cantilever beam with an end support B, how you would solve that. I introduced a specific notation for solving these things. Basically, the idea is to calculate the displacement, to first of all decompose the indeterminate structure into a determinate structure plus a redundant force. Okay, so the objective would be to try to find what this redundant force would be. So the idea is that you find the displacement under the given load at the redundant point, and you find what is called the flexibility. And flexibility FBB in this case is written as FBB because the first B denotes that I'm trying to find the displacement at the point B, and the second B denotes that there is a unit load applied also at B. And I think this notation was hopefully a little more clear in the other example with 2 degrees of indeterminacy that I showed, where we had flexibilities FBB, FCB, FBC, and FCC. So these are flexibility coefficients that you can calculate by applying a unit load at a certain point in the structure and measuring the displacement at all the degrees of indeterminacy. Okay. And again, first subscript is the location of the displacement, and second subscript C is the location of the redundant load. So keep this in mind, and I think last time I also, just about when we finished, we were talking about these Maxwell theorem, reciprocal theorem, and the Betti's law, which says simply that work done by a set of forces A as they go through displacement caused by a set of forces B is the same as the work done by forces B as they go through displacement caused by forces A. So that's where we were about, and I was telling you that the fact that this reciprocity theorem exists helps us in the way that it allows us to say that this flexibility matrix would be symmetric, which means we need to calculate only roughly about half of the coefficients. But even then, I told you for big systems, even half those coefficients can be quite a lot to calculate. So later on, a little bit later, we'll see how to systematically calculate these coefficients, not by hand, but through a computer program, which I'll provide to you, and we'll go through those things in more detail. Okay, so let's do a couple of examples on this force method. Um, so here's one. Here's a continuous beam with supports ABC. Clearly, it is indeterminate with degree of indeterminacy. How much? What's the degree of indeterminacy of this structure? 1. So if I remove one of the supports, it becomes a simply supported beam, right? Um, and there are some loads applied to it, and the problem simply says find all the reactions ABC. Clearly, it's an indeterminate structure. You cannot use only equilibrium to find it. And once you find the reactions, you need to draw the resulting shear force and bending moment diagram. Okay, so going by what we had just discussed right now on the previous page, that if you have an indeterminate structure, you remove a couple of the supports and you apply a redundant force there and solve and so on. You can do that, but there might be a better way to solve this particular problem. The key thing here is to choose an underlying determinate system in such a way that it simplifies your computations. So as this figure shows, one might be actually tempted to remove this support B and just solve it as usual, which is great and fine. You will still get the same answer, but it would end up being a longer method, right? A better method actually is to imagine this beam as being part of, as basically two simply supported beams. Okay, so I'll make a cut here to make those two segments A to B and B to C independent. Now they are both two simply supported beams, and I have still only introduced only one redundant moment in this case, right? So redundant, instead of a redundant force, I'm introducing a redundant internal moment. And the benefit of that, of course, is that now the left-hand side structure becomes symmetric, the right-hand side structure becomes symmetric. All I need to do is to find what that internal bending moment M would be to try to make sure that the displacement under, or the rotations under this load and this load get cancelled off by the moments applied due to these redundant moments, that the rotation due to these redundant moments. Okay, so here's how we're going to proceed with that. I just laid out these steps 1, and now we are laid out step 1, and now we are going to proceed with this step 2 of finding out the rotations really at the support B. So first, I'm going to draw what might be the deflected shape under these actual loads. So this might something deflect like that. This might deflect like that. And if I were to draw the cross section of the two ends, this cross section might look something like these. There, so the cross section at these two ends, if we do separate them, then the cross sections would look something like that. And I'm going to call the angle between them delta theta B, which is basically the discontinuity or incompatibility because I broke the beam right there. Okay. Now, in the same way, I'm going to draw the deflected shapes of the other redundant moment due to the redundant moment. So the redundant moment deflected shape might also look something like that. And if I draw the cross sections, once again, those cross sections would look something like that. And the angle between them, I'm calling delta theta B prime. So the compatibility equation simply is that delta theta B plus delta theta B prime should be equal to 0, right? So the amount of this rotation would depend upon this moment. And the idea, of course, is that I need to apply the right amount of moment so that I close the rotation back together for both those beams and they behave like a continuous beam. Make sense? Okay. So how do I find this delta theta B? how do I find delta theta b for the first sub-problem? We can use any of the methods that we have learned, right? Principle of virtual work, Castigliano's theorem, or your moment area theorems, or whatever. So we're going to assume now that you know any of those methods can be used, and we are simply going to make use of some tables actually that are given in your book. Let me see if I can turn this on. And okay, so if you look in your book, here on the first page, for this problem, for the left-hand side sub-problem, I have a simply supported beam with a point load in the middle, which, let me zoom in here. So which clearly is something like that, right? And what this table tells me is that the maximum displacement is PL cube over 48 EI at XL over 2, which is in the middle. And the maximum rotation is PL square over 16 EI, of course, at the ends. So this is something that I'm sure you can calculate by using any of those methods, but it's just easier, of course, to make use of these tables whenever we can. Another point here is that if we had not made this redundant choice, instead if we had removed support B, it would have been a much more complicated problem, something that for which we cannot use these tables. So even for your homeworks, feel free to use these tables whenever you can. If you can't directly use these tables, you will actually have to find the displacements or rotations at those points using any of the methods that we've learned. So for this problem, delta B or theta B at this point is PL square. So I'm just going to write that, PL square over 16 EI. That's for the simply supported section. And similarly, if you move up in this table a little bit, you see a simply supported beam with a uniformly distributed load, and theta max for that is WL cube over 24 EI. So I'm just going to write that as the second displacement, omega L cube over 24 EI, just directly reading off of those values. So let me turn this off. At that point, I can find the change in rotation due to this cut, which would simply be 12 times 12 square divided by 16 EI plus omega is 3 kip per feet, and L again is 12 cube divided by 24 EI. And if you calculate that out, you should get 324 over EI kip feet square. Okay. So that's the displace or the rotation if both of those beams act independently. Now, the second part is to try to find the flexibility due to this redundant moment. So that's step 3, which is basically saying find displacements due to the redundant loads. It can be find rotations. So maybe I'll write that too. Either displacements or rotations due to redundant moments. So in this case, since I've applied a redundant moment, once again, I'll go back to that table. Go back to that table, and if you scroll all the way down, there's a simply supported beam with an end moment, right? And that rotation, there are 2 rotations given, theta left and theta right. So what rotation should I choose? Theta right, because of course I want the rotation at that point. Theta right is ML over 3 EI. Okay, so I'll write that. ML over 3 EI for this part. How about this guy? Should I choose left or right? Right again. Why is that? Of course, because it's just a mirror image of the same structure, right? In this case, the moment is being applied to the on the left side, so the rotation at the end at which the moment is being applied is indeed ml over 3ei, right? So that's another ml over 3ei, and if you calculate that out, we get 2 ml over 3ei equal to 2m times 12 feet divided by 3ei, which of course is 8 m over ei. This should be let's see, does that unit make sense? Feet, right? So the moment would be in kip feet. Yep. Okay. So now that I have these two rotations, the rotation under the applied loads 324 EI, 324 over EI, and the rotation due to the redundant moment is 8 m over EI. All we need to do is to enforce compatibility, which, as I said, is simply that delta theta B plus delta theta B prime is equal to 0. And which helps me to find m is equal to 324 over EI divided by 8 over EI. EI's cancel off, and what I get is, I believe, 40.5 kip feet. So the redundant moment, the redundant internal moment is actually should be minus 40.5 kip feet. The negative sign also makes sense because for a beam with an internal support like this, you would indeed expect a negative moment at the internal support, right? So once you have done that, the second part of the problem says find or draw the shear force and the bending moment diagram of the actual beam, the actual indeterminate beam. And that's also not too difficult to solve. You already know what the response of the actual load system is. You know the internal moment is negative 40.5. All you need to do is to just superimpose or add those two results together. So we'll do that. First, we'll draw the shear force diagram due to the actual load system. And just by going by our convention, we go up by 6. And across out here, then minus drop by 12, go back here and up by 6, go up by 18, and then drop down to minus 18. So let me write those values: 6, minus 6, minus 6, and this would be 12. Is it 18? Oh, because, yeah, so there's actually there's two forces there, so minus 18, and that's the shear force diagram only due to the actual loads. And finally, the shear force diagram due to these redundant moment, that would be, I'll draw that in blue or purple, minus 3.35 and um, across all the way here, back to 3.35, and up again by 3.35, and go all the way across 3.375. Right, those values too. I'll not draw the resultant diagram. It's just a sum of these two. Okay. Same thing for the bending moment diagram. On the left-hand side, you can see that the bending moment diagram would be a triangular positive diagram actually. So we'll get 6 times 6, that should be 36, down back to 0. And for the uniformly distributed load, it should be a quadratic curve like that. So this is 36, and that center point is 54. And similarly for the redundant moment, we have starting out at 0, we go to a negative moment minus 40.5, and then go back down to 0. Okay. So again, the critical steps here are basically to make sure that once you, if you have an indeterminate system, that you decompose it into a underlying determinate system that is easy to solve. In this case, the easiest thing was to actually cut the beam and have the internal bending moment as the redundant quantity. Once you do that, you can use these tables, or you can calculate by hand whatever rotations are needed. And compatibility is what allows you to calculate those redundant forces. I'll also mention something here. As opposed to displacement compatibilities, this quantity L over 3EI, L over 3EI, can anybody tell me what that is? Not stiffness, but flexibility. It's the inverse of the stiffness, right? Because this is the rotation that you would get if you applied a unit moment at that point. Similar to the displacement that you would get at these points if you were to apply a unit load, which we are calling FBB in this case. For rotations, we are going to call them alpha B B, and I'm going to call that 1 because, or left, for the left side, and similarly it's alpha B B from the right side. So the flexibilities for displacements, we are denoting them by F, and just to be consistent, this is the notation that's used in your book as well. For rotations, the flexibility that we are the symbol that we are using is alpha. But again, the subscripts denote exactly the same thing. Rotation at B due to a unit moment at B. Rotation at B due to unit moment at B from the left and the right. Okay. Any particular questions on this problem? Okay. Um, let's take another problem, and I'll let you take a couple of minutes to try to set up the problem. You don't need to completely solve it all the way to the end. See if you can figure out what the how you would decompose it and what the bending moment diagrams turn out to be, and all the displacements and flexibilities. So again, the problem is this frame, which is fixed at C with a roller support at A. Okay. And the question simply says, find the reactions and draw the shear force and bending moment diagrams. And I've already decomposed that into a underlying determinate and redundant system for you. Let's take a couple of minutes, see if you can set it up correctly, and then we'll solve it together. Not an in-class exercise. And feel free to discuss with your neighbor. Yeah, there won't be a table directly for this problem, so we'd have to use one of the methods that you've learned. All right, what's the first step that I should do? Who wants to volunteer here? Or maybe I should start picking names.
Figure out the bending moment diagram.
Okay, let's figure out the bending moment diagrams. So why don't you go ahead, Nafal? What does the bending moment diagram for this look like?
It's minus 80 on the vertical member.
Minus 80 on the vertical member. That makes sense because this is 10 times this distance 8. So I'll draw that on the negative side. And I'll draw that in blue because this is the actual load. So minus 80. And
minus 80 is 0.
right, so if I take a cut somewhere here, then the moment, internal moment at that point would just be 10 times that distance. So let me label that. I'm going to call that x1, and it would just increase linearly with that, and I'm drawing negative because the displaced shape of this would look something like that, right? Maybe I'll draw that too. Something like that would be the displaced shape. Really looks like a frowny phrase. So we have a negative moment there. I'm going to call that minus 10x1. And for AY, actually I should do that. AY times this structure where I apply a unit load there. So if I apply a unit load there and take whatever response I get from that right hand side substructure, multiply that response by the unknown redundant force AY, then add it to the original determinate system, then the sum of these two should be equal to my indeterminate problem. And that's the logic here. So if I apply a unit moment here, it would of course bend up, and I would get some, maybe I'll draw that too. So it would bend up something like that. And in this case, the bending moment diagram, I'll draw it in red, and you'll see in a minute why. I'll draw it as positive, increases linearly all the way up to there. So I'll call that point X, and that would be positive 1x. And at the end, it would also be a positive moment of this 1 times this entire 16, which is 16 kip feet. So these are the two bending moment diagrams that I have. Using these two, can I calculate what the displacement would be at point A? Maybe this is the displacement that I want. I'll mark that here as well. Delta at A is what I want. So how do I do that? Tables are not going to help me in this case. If I wanted to use the virtual work method to find the displacement at A for this determinate structure, how would I do that?
Are we assuming that vertical displacement at B is 0?
Vertical displacement at B is 0. No, we are not assuming that. We're not assuming that. That's right. So if we use the virtual work method to find the displacement at A, what I would have done would have been to apply a P prime here, correct? Instead of applying that P prime, I could just take that P prime, multiply it with a negative sign, and apply a unit load instead of P prime, because P prime at the end all does get cancelled off. So I can apply a P prime here or a unit load here. And the response of this system is really the response of the virtual system if I wanted to calculate the real displacement here. Make sense? And that's another another benefit of using using the force method, because you are not really doing any extra calculation by just applying this unit load here. So to calculate displacement at A, I would have virtual moment. So I'll write that here. And I'll set up my integral in such a way in terms of x1 actually, because the left half of this real system is really 0. So I'll use x1 and I'll write that integral as 1 times x1 plus 8. That's the virtual bending moment, right? That's the virtual bending moment in this half. 1 times x1 plus 8. Hope you see that. And times the real curvature. The real curvature is just the curvature due to this part, which is minus 10 x1 divided by EI. And I integrate that dx1 from 0 to 8 feet. That's the displacement due to this component. And I need to add to that the displacement due to those two vertical components. So I'll do that. Plus, again in red, which is 16. That's the virtual bending moment times the real curvature, which is minus 80 over EI. That's dx. Maybe x is not a good variable, so let's call y. Integral from 0 to 10 feet. Is everybody convinced that displacement at A is equal to this long expression? Well, not too long, but this expression, virtual bending moment times real curvature integrated over the length for both the segments. That's all there is to it. Okay, yeah, let's see how we do that. So if I were to try to write the expression in this part of the structure, okay, I know that my x1 starts at the middle point. So when x1 is 0, I already have a moment of 1 times 8, correct? So I need to start it with 1 times x1 plus 8, because when x1 is 0, I get the right moment, and then when x1 is 8, I get the correct moment, 16 out here. Okay. Yep. Frederick. We are neglecting the left side because there is no real bending moment here. So even if I had included that in my integrals, the real curvature would have been 0 in that part, right? Good. More questions? Okay, so hopefully you can all see that the virtual bending moment times the real curvature integrated over the length, that's the displacement here. And without actually going through too many steps, maybe I'll just do one step here. So I get AT over EI times x1, and that x1 squared over 2 integrated between 0 to 8, and plus, actually that should be a minus here, this should also be a minus, and I have minus 10 over EI, inside is x1 squared, so that becomes x1 cube over 3, again between 0 to 8, and the right hand side is minus 16 times AT over EI integral y between 0 to 10, and I'll let you verify that those integrals turn out to be this much. And what we get here is this 107, well, 17,000 minus 17,000 over EI. Why did we get minus here? Right. So the actual displacement is down, whereas we applied the unit load up, or the P prime pointing up. So we should indeed get a negative there. Now the second part is to try to figure out what the flexibility at the free tip A is under a unit load at A. Okay. So the first is denoting the displacement at A, the second A denotes the load at A. So how do I find that? How do I find FAA? How can we find displacement at point A due to a unit load at point A? Say again? Again? We have set up the bending moment diagram for that, but we have not yet actually found it. Say it again? Okay, so yeah, we can use again the virtual work method. So if I apply the virtual work method to find the displacement at A due to a unit load at A, in this particular case, it's great because the real system is right here, for which we have already found the bending moment diagram. And what's the virtual system? The virtual system is exactly the same thing, right? So the real and virtual system are both right here. And in this case, all we need to do um, is to write the virtual bending moment that's 1x. I'm not using x1 right now because I do need to start with x. And the real curvature is 1x over EI. Integrate from 0 to, that's 16, I believe, and plus the virtual bending moment is 16 times the real curvature is 16 over EI, and dy integral 0 to 10. And if you do that, you get these numbers. Okay. At this point, all we need to say is that compatibility, that what would be the compatibility equation? What would be the compatibility equation? Okay, so essentially we are saying that delta A, which is the displacement due to the actual loads applied, plus let me say delta A prime, which is the displacement due to the redundant loads applied, and actually since it's in the opposite direction, I'll just say minus, equal to 0, which is saying simply that delta A minus AY, the unknown, times FAA is 0, which simply means that delta A or AY is equal to delta A divided by FAA, which should turn out to be 4.35 kips. Just dividing this value, dividing the actual displacement by the flexibility. And we get that the redundant force is 4.35. Once we have that, the shear force and the bending moment diagrams are also not too difficult. It's pretty much the same way. Shear force diagram for the left part, I'll draw that in blue. Minus 10, go back up, and the vertical force, let me draw that as 4.35. So we get that's the shear force diagram for the real and the redundant systems. You add them and you get the resultant shear force diagram. And similarly, for the bending moment, this is 4.35. That value turns out to be 69.6. That's the same positive 69.6 here, and we've already calculated the bending moment due to the 10 kip, which is minus 10x1 and minus 80. So sum those two and you get the bending moment diagram for the frame. Okay, so not terribly complicated, but the fact that we use the virtual work method and not any tables is not terribly more complicated either. If you are able to use the tables to calculate these flexibility coefficients, great. But not all problems are as simple as those tables. And even if they are not simple as those tables, you can see right here, once you draw the bending moment diagrams, the displacements and the flexibilities are practically one-line integrals. Okay. Any questions on this, either of these two problems? So I'll let Dr. Liu do more problems on Friday for the force method. And what we'll do is jump into the force method for trusses, okay, which is basically on the handout that you should have received today. And for trusses, for indeterminate trusses, really, the process is also very similar. But in this case, you do need to make sure that you account for all the energies correctly. So let me highlight, kind of outline how this goes. Here's, for example, an indeterminate truss, right? What's the degree of indeterminacy for this truss? For this truss with a cross and right through the middle, there's no point here. There's no joint here, okay? The joints are only at A, B, C, and D. So, for example, if I remove this member, that immediately becomes a determinate truss, right? If I add this member, of course, it's an indeterminate truss of degree 1. You can obviously have indeterminate trusses of higher degree, but in this case, once you determine which members you want to cut or which members you want to remove, you can see that if I had maybe cut this member AC and applied this load, what I would get is a deformed shape like the blue outline here, right? And under that force, the force in this member that we have cut would be zero, right? This member we have cut to make it determinate. So under the application of this 4 kilonewton load, both these parts of this member would be zero force members, and we would get some deformation like that, which means that the two ends of this member cut would not be compatible anymore. Okay, and the problem now becomes is what particular internal force on this member that we have cut, what internal force should I apply so that I can get this delta AC plus this delta AC prime is equal to 0. Right? So it's the same idea, but the implementation is slightly different. Um, so let's take a look at this example here. Three-member truss. Is this determinate or indeterminate? Indeterminate to what degree? How do we find the degree of indeterminacy of this? 3. Why is that? So it looks like we have two unknowns here, two unknowns here, two unknowns here, 6 unknowns. I agree. But how many equations do I have? A total for a two-dimensional problem, a total number of equations is, of course, sum of forces in x, y, and moment equal to 0. But that holds only when your structure is not a mechanism, right? If I disconnect these three supports here, this structure by itself cannot hold its shape. It's a mechanism. Ever heard of that? So in this particular case, what you would have to do is to disconnect all these three members separately from each other. You would have, in that case, three separate structures. 3 times 3, you would have a total of 9 equations. And the number of unknowns you would have would be 2. So those 6 reactions definitely. But there would be 4 internal forces between all these 3 parts. And I can show you the details, but maybe I want you to figure out how that would work. Maybe another way, very simple way to think about it is if I were to remove this member BC, what would happen? If I remove this member BC, then it would still be a perfectly supported structure. There won't be any movement at D. There won't be any movement at A. This would be very similar to the homework 1 problem that you all solved, right? Two-member truss with a point load applied at the free point. That's a determinate system. So if I'm removing one member BC, degree of indeterminacy is 1. Right? So if I remove one member BC to make it determinate, it becomes the degree of indeterminacy of this problem is 1, which is basically what I'm doing here. I'm saying that if I were to cut this member BC right here, I apply the actual load BC. Under the action of this actual load BC, these two cut ends would either separate or overlap. They would have some displacement. And then if I apply a unit load here, I would get some opposing displacement to that. And if I multiply that with the right amount of force BC here, then that actual force system plus BC times the redundant force system should give me the actual response of the indeterminate system. Okay. All right, so I'll let you think about it, and then we'll continue this problem on Wednesday.